Let's imagine that we have a point charge sitting at the origin. So according to Coulomb's law, it's going to create an electric field that points outward in all directions, and it drops off with the square of the distance, right? So 1 over r squared. And now we can calculate something called the divergence. So what the divergence measures is basically how much a field is spreading out from a specific point. So in our case, only from the origin. If we calculate the divergence of this electric field in spherical coordinates, we end up with the derivative of 1, which basically makes it 0. We can also calculate the flux of this electric field, which is basically how much an electric field passes through a surface. So if we make an imaginary sphere around the origin with the charge inside, the flux follows Gauss's law, which says that it is equal to the charge divided by the permittivity of free space. So the interesting thing happens when we look at the divergence theorem, which was again proven by Gauss. What the divergence theorem states is that the total flux of a vector field across a closed surface, so like the electric flux, has to equal the sum of all of the small divergences within the volume in that surface, right? So basically you're adding up all the little sources and you get the total outward flow. But wait, doesn't that mean the right-hand side of this equation is equal to 0? That's where our problem comes. To solve this, we need to look at something called the Dirac delta function. The Dirac delta function isn't actually a function. Mathematicians call it a distribution, but for our purposes, we can treat it as one. So the Dirac delta function has a distinct peak at the origin that shoots up to infinity, and everywhere else it is equal to 0. And an interesting property of this is that if you take the integral from negative infinity all the way to infinity, the total area under this graph is equal to 1. Now, if we have a normal function, f of x, and let's say that we multiply it to the delta function. Since everywhere else the delta function is 0, except for x equals 0, that's the same thing as multiplying f of x as 0 with the delta function. So, if we want to evaluate the integral of f of x times the delta function, that's the same thing as pulling out f of 0 and just evaluating the integral with the delta function on its own. And we know that is equal to 1, so the whole thing is equal to f of 0. So now we can put the delta function into 3 dimensions, which is basically multiplying the delta function as a function of your basis vectors in all 3 dimensions. And again, if we take the triple integral of this 3D Dirac delta function, it is equal to 1. And as you expect, if you multiply a function to it and take the triple integral, that's the same thing as the function evaluated at the origin. So it turns out that the divergence of the electric field from the point charge that we had earlier is equal to the charge divided by the permittivity of free space, as we saw earlier, times the 3-dimensional delta function. What this means is that everywhere that's not the origin, the divergence of this electric field is equal to 0, but at the origin, the divergence is equal to infinity. So now, if we take the triple integral of the divergence, that is just equal to q over epsilon naught, which is equal to Gauss's law as we saw earlier, and the divergence theorem still holds. This may not seem like a very extravagant result, but the delta function has so many uses in physics when modeling things that have spikes. Some examples include modeling impulse, which is like a force acting over a small time interval, describing the position of quantum particles, which are described by position eigenstates, and God forbid you study quantum field theory, because it appears in Green's functions.